So the last part of circuit analysis is really to look at Kirchhoff's rules and kind of put everything together. So first we're going to look at the loop rule, which is KVL, Kirchhoff's voltage loop. And what you're going to do is there's sort of different conventions that you do. I kind of do voltage negative drops as I drop across each resistor. And so what you're going to do is you're going to just say there's a current drop across each resistor as it goes around the loop. So apply the loop rule to A, B, C, D, E, and then I go F, G. So I'm going to go like this all the way back, H, I, J, A, and then go back down to here. And we're going to use these currents that we established, like I1 here. So we're going to say I1 times R1, so negative I1 R1. And then every time we go through a battery and we gain voltage, we're going to add in 24 volts. Oh, actually, so instead of R1, I'm going to put in I1 times 5, because this is 5 ohms. I1 times 5 plus 24 volts. Then we're going to drop R1, so minus I1 times R1, which is 0.1. So 0.1. And then we have I1 going through R5 minus I1 times 20. Then we're going to go through this loop. And this loop you have to be careful because the current going into this resistor is I1 plus I2. So we're going to do I1 plus I2. I1 plus I2, and it's going to drop 0.2 ohms. And then here it's a voltage drop because this is the positive terminal and negative, so we're going to drop 36 volts. So I'm going to do minus 36. And then here we're going to drop across. You always drop across a resistor. And this current is actually instead of I1 plus I2, you could have used I3. It doesn't really matter in terms of setting up your equations. You could have replaced with I1 and I2, or you could have just said this current is I3. So I'm going to do I3 there. And then I3 drop through there, so it's minus I3 times 0.05. And then we're going to gain 6 volts, because this is the positive terminal, this is the negative terminal. I'm going to gain 6 volts. Okay, and then I'm going to drop I3 times 78 here, minus I3 78. And the sum of that has to be 0 because we came back to where we started. Okay, so that's 36. And you can kind of simplify. You can combine all the I1s, combine all the I3s together if you wanted to. For 37, we're gonna do AK L E. So we're gonna go like this through the loop, like this direction. Okay. So here I'm gonna gain 48 volts. So I'm gonna add 48. And then I'm going to drop across here. I'm going to drop by I2 because I2 is going from right to left. So it's going to be minus I2 times 0.50 minus I2 times 40. This resistance right here. Then we're going to go up here and it's going to go I1. But you have to be careful because I1 is going in this direction. Okay, so this is really like it drops I1, but really I think of it as this current is negative I1. I think of it that way. And I always want the current to flow in the direction that I'm moving. That's just how I do it. So it's going to be minus negative I1 times R5, which is 20. So you see that would make it plus I1. So the voltage is going to increase if I'm going I1 in this direction, or if I go negative I1 in the opposite direction, in the direction of my loop. Is that your equation will still be the same. It'll still be plus I1 times 20. But I find it useful to just have a standard convention where I'm always doing in the current in this direction. So this is negative I1, right? Because I1's going from left to right, so negative I1's going the other direction. Minus negative I1 times 0.1. And then, because we're going in this direction, we are dropping 24 volts, right? Because this is the positive terminal, negative terminal, and so we're going to drop 24 volts. Whenever I drop, minus 24. And then minus negative I1 times 5. Sum of that equals 0. So that is just doing the KVL computation directly. So we're not going to simplify, we're not going to solve the circuit, we're just simply going to do the KVL for this problem. Okay, consider the circuit shown below. Find the voltage across each resistor. What is the power supplied by the circuit and the power dissipated or consumed by the circuit? Okay, so here's one where we can do our, let's do it as KVL in this case. Now, one thing we could have done is collapse the resistors and stuff like that, but we're going to do the KVL. We're going to start down here. Okay, and I'm going to move up in this direction. So say the current flows like this, I1. Okay, I don't know the actual direction of the current, but I'm just going to use I1 for my loop equation. Okay, so I'm going to say, first I'm going to gain 12 volts. I'm going to subtract I1 times R1, which is 10 kilo ohm. I'm going to subtract I1 times 20 kilo ohm, because I'm going to go through this resistor here. Then I'm going to drop through this resistor, so minus I1 times 10 kilo ohm. See, in this circuit, the I1 just flows like this, so I'm always dropping voltage. Here I'm going to drop 24 volts, because this is the positive, this is negative. I drop 24 volts. And then I'm going to drop I1 times 10 kilo ohm. And then I'm going to drop I1 times another 10 kilo ohm. And that has to equal 0. So if I combine all the I1s and the constants, so the 12 minus 24 is a constant, so that's minus 12. And then I have minus I1 times 10 plus 20, 10k, plus 20k, plus 10k, plus 10k, plus 10k, equals 0. So this is 10, 20, 30, 40, 50, 60, it's 60k. So I have, and I move the 12 to the other side, so I get negative I1 times 60k is equal to positive 12, and so I1 is equal to negative 12 over 60k. This is this goes into it 5 times, so it's like makes it 0.2 milliamp, I think. Let me just do it 12. So I get negative 0.2 milliamps. So because I got a negative current number, what that means is the current is actually going this direction at 0.2 milliamps. Okay. And so so I guessed wrong. And it makes sense. This voltage is higher, so the current ought to have been flowing this way. But because I got a negative number, it just means the current's actually flowing in this direction in the positive way. Okay, so that's the so now we need the voltage across each resistor. The voltage across each resistor is V equals IR. So I'm just going to do 0.2 milliamps times 10k. So which ones are the 10ks? R1, R3, R4, and R5. They're all going to have the same voltage because they're going to have the same currents going through them. It's equal to V3, V4, V5, and that's equal to 0.2 times 10, 2 volts. It's 0.2 milli times 10 kilo ohm. So that's, just to be clear, it's 0.2 times 10 to the minus 3 times 10 times 10 to the 3. That's equal to 2. Okay, and then V, the only resistor that has higher is V2, and that would be 0.2 milliamps times 20 kilo ohms, and that's 4 volts. Okay, and then what's the power dissipated or consumed by the circuit? It's just basically the current. I would do the power is equal to I squared R, because all of them are going through the same, has the same current flowing through them. So I'm going to do 0.2 milliamps squared times R. The resistance, sum of the resistances is 60k. So if I multiply that, 0.2 e minus 3 squared times 60 e3 is 0.0024 watts. Now, how much is consumed? That's how much is consumed by the circuit. How much is provided by the supplied by the circuit? Well, you see, the current is flowing out of this way. Current flowing out of a battery is sending power. So this is sending a power of 24 times 0.2 milliamps, right? P is equal to IV. And so this one is doing 0.0048 watts. But this battery is not sending out power because it's absorbing 0.2 milliamps of power. So this power is negative 0.2 milliamps times 12 volts. That's how much power this is absorbing. And that's 0.0024 watts. Negative though, because it's absorbing power. So from these sources, the amount that it's sending out, and actually this one is absorbing. So you would actually include this as part of here. So this one actually should have been in here. So we would say this is absorbing, all the resistors are absorbing this power. This voltage source is absorbing this power, or consuming. So we're sending out this much power and we're absorbing this much power, which is 0.0048 watts. The sign really only tells you whether or not the power is being absorbed or consumed. Okay, but like, so we added the 0.0024 plus the 0.0024 here to get, this is how much is consumed. It's the R's and the 12 volt source, because it's not sending out power. And then what is sending out power? So this is the only thing sending out power, delivering power, supplying power. Thanks for watching. If you enjoyed this video, I go through a lot more of these exact kinds of problems with much longer videos on my website. It's entirely free. Check out the link in the description below.